Hi dear students, welcome to today's online class. This video is on a very interesting area of spectroscopy, molecular spectroscopy, that is problem solving in spectroscopy. That is, if you are given a spectroscopic data, a spectral data of a molecule, and along with the molecular formula, we can deduce its structure by analyzing, interpreting various spectral data, that of UV visible, IR, NMR, etc. Let's take the first example, the first question. The question is, deduce structure from the following data. The data given is, molecular formula is given as C4H8O. Okay, then IR data or this compound is strong band at around 1700 centimeter inverse, and says no band in the region 2900 to 2700 centimeter inverse. See, in spectroscopy, absence of a peak is also very informative, very valuable. Now, NMR data given for this compound is like this. At chemical sheet value 2.8, there is a quartet corresponding to 2 proton quartet at 2.8. At 2.15, there is a singlet equivalent to 3 proton, and at chemical shift 1.1, there is a triplet corresponding to 3 proton. This is the data given. So let us make use of this data to deduce the structure. What is the step? What are the steps? First thing is, look at the molecular formula and identify the degree of unsaturation in the formula. How many pi bonds are there? Is there any pi bond, or if the molecule is saturated? That can be easily identified by looking at this hydrocarbon part. You neglect oxygen. Here C4H8, it is fitting to the formula CnH2n, that of an alkene, correct? If it is saturated, it would have been CnH2n plus 2, then of alkane, then it should be 10, hydrogen should be 10, but it is 8, so it means what? 2 short of hydrogen, 2 hydrogen short, that is equivalent to 1 pi bond. So the degree of unsaturation is 1, what we call degree double bond equivalence. We also call it double bond equivalence, or degree of unsaturation is 1. That means the molecule contains 1 pi bond, correct? Now, since there is oxygen, what are the possible functional groups? If oxygen is there, the possibilities are alcohol, but it doesn't have, see, first of all, let us consider double bond containing functional groups. So it can be aldehyde, it can be keto group containing 1 oxygen. It can be alcohol or ether, provided there should be a double bond between carbons. So that is also possible. Okay. So OH is possible, ether is possible, but then pi bond should be there between carbons. Now look at IR data. IR says strong band at 1700. What does it mean? So this implies presence of which group? Carbonyl group, CO group. So CO is possible. That means we can rule out this. Now it can be aldehyde or ketone. Okay. Now no band between this range. What does it mean? Between this range, no band means it is not aldehyde, because aldehyde is characterized by 2 peaks around 2700 and 800, like that. So it is not aldehyde. So the compound is ketone. We should interpret each data. So not aldehyde. So we fixed the functional group. Now, NMR data will give you the complete structure. Now, here at 2.8 there is a quartet for 2 proton. What does it mean? 2 proton quartet means CH2 group has a signal which is a quartet. Why? Because it has a neighboring CH3. That's why. See, if there is a CH3, see, you know that multiplicity of a signal indicate the neighboring proton. So CH2 become quartet means there is a CH3 nearby, and that is supported by this NMR signal. At 1.1 there is a triplet for 3 proton, that is 3 proton triplet because of the CH2, right? 2 proton quartet because of this CH3. So whenever you see such a data, that is 2 proton quartet and 3 proton triplet, sure, mostly it contain an ethyl group. It contain this structural unit. Now regarding this, okay, now what about the rest? There is a singlet for 3 proton. See, 3 proton singlet means what? There is a CH3 which appear as a singlet because there is no neighboring proton. Okay, now this is the NMR data. So this is interpreted like this. We can just connect all these information to get the structure. Only there are 4 carbons. Now it's very easy. So CH3, CH2. Now look at the chemical shift of this quartet, CH2 quartet, 2.8. You know there is its keto group, so keto group has to come in between. So when it come like this, now what is left over? This CH3 group, which is a singlet because there is no neighboring partners. Now once you deduce the structure, arrive at the structure, you should again check back, like this CH2 quartet at 2.8. Why? Because we know the chemical shift of CH2 connected to CO is around 2 to 2.5 or 2.8 it comes, and this singlet CH3 is also 2.15 because it is also connected to CO, so it is de-shielded. Both these are de-shielded, and CH3 is, as usual, it's aliphatic CH chemical shift is around 1. So we arrive at the data. Okay, so after you deduce the structure, you should again compare or check with the data given. Let us now go to the next question. The next one, the second question, molecular formula of the compound is C3H6O2. IR data, sharp peak is there at around 1725 centimeter inverse. Broad peak, this is the nature of the peaks. Some are broad, some are weak, some are sharp. Broad peak between 2500 to 3500 centimeter inverse, and there is also another peak at around 1000 to 1300 centimeter inverse. This is the IR data. Now NMR data, at chemical shift 11.6 there is a singlet corresponding to 1 proton. At 2.4 there is a quartet for 2 proton, and there is at 1.0 there is a triplet for 3 proton. Okay, let us try to deduce the structure. See, looking at the formula, what about the degree of unsaturation? C3H6, so it is unsaturated. How much it has to be if saturated? CnH2n plus 2, so 3 into 2 plus 2, so it has to be 8. Okay, but it is 6, so again there is shortage of 2 hydrogen, which is equivalent to 1 pi bond. So the double bond equivalence or degree of unsaturation is 1. Now there are 2 oxygens. What are the possible functional groups? Functional groups possible are, it can be as before aldehyde and also another oxygen. There are 2 oxygen, right? There cannot be 2 aldehyde because then there will be 2 pi bond. And it cannot be 2 ketone also. It can be an aldehyde group or ketone group. It can be with an alcohol group also. So there is a chance for OH also. And there is another chance that it can be an acid group because C double bond, there is a 1 pi bond and 2 oxygens are accommodated. It can be even ester also, COOR, like that, accommodating 2 oxygen. Now, let us go to IR data. In IR, there is a sharp peak corresponding to which one? 1725. What does this indicate? Of course, there is a keto group, CO absorption is there. Okay, carbonyl absorption. There is a broad peak 2500 to 3500. What is this? A very broad peak in a wide range indicate it could be acid. It is OH stretching, which can vary due to hydrogen bonding. It could be acid. And it is now confirmed by NMR data. Look at this. At 11.6, there is a singlet for 1 proton. You know, that is for carboxylic acids. So it could be carboxylic acid, which is supported by this factor, this NMR data. And also this one. You understand? So the compound could be carboxylic acid. And there is a peak at 1000 to IR peak at 1000 to 1300. What is it? It is due to this C single bond O stretching. You know that it comes in fingerprint region. So this is confirmed. Now what about the rest? The remaining NMR data, it's very similar as in the previous example. There is a 2 proton quartet at 2.4. That means there is a CH2 2 proton, which is a quartet. That means it is connected to CH3, and it is confirmed by the next data. 3 proton triplet. 3 proton signal is a triplet due to this one. So this is becoming a triplet. This is becoming quartet. And again, this quartet is at a chemical shift 2.4. It is desheated because it is connected to carbonyl group. Now, of course, this is a very simple molecule, C3, only 3 carbons. So it is all confirmed now. CH3, CH2, COOH. We can again verify. Everything is now verified actually. This is verified. It is a carbonyl group, has an absorption at 1725 for carboxylic acid. And OH, presence of OH is supported by this IR peak, a very broad peak due to hydrogen bonding. Okay, and this carboxylic hydrogen proton is seen as a singlet at very large chemical shift 11.6. So this is the structure of the molecule. Right? Now the last one. We discuss one more example. A little different one. Just see what is the difference. Here the molecular formula given is C8H8O. Then IR data, there is a sharp peak at 1700. There is another peak at 3150. No peak, see, no peak at in the range 2700 to 2900. There is a sharp band at 1600 as well as 1475. and there is another peak at 3000. There are so many IR information. Now in NMR there is a 5 proton multiplet. 5 proton multiplet is seen at del value between 7 to 8, and then there is a 3 proton singlet at the del value 2.3. Okay, let's come to the deduction of structure. Look at the molecular formula. C8H8, carbon hydrogen ratio is almost 1:1. That means compound is highly unsaturated. When you see such ratio, you can think of aromatic compounds, especially when number of carbon is more than 6. So it is something like benzene related compounds, because benzene is C6H6. So high degree of unsaturation. So the compound could contain benzene, right? So that can be verified with the rest of the spectroscopic data. You can see there is peak near 3150 that correspond to the aromatic CH stretching, right? Then there is a peak at 1614.75 correspond to aromatic CC stretching. Okay, so benzening is there. Now this, and there is oxygen. So what about the functional group now? Presence of oxygen implies it could be a keto group or aldehyde group, right? Or it can be alcohol or either also. Let's verify. But see that there is a peak at 1700 indicate it is an carbonyl compound. It can be aldehyde or ketone. It cannot be acid or ester because it needs 2 oxygen. So aldehyde or ketone. Then no peak at this range indicate what? It is not aldehyde. It is ruled out. So the compound is an aromatic ketone. Only 8 carbon atoms. 6 carbon atoms are in the ring and 1 carbon, that is a carbonyl carbon. Now only 1 carbon is left. You can look at the Nmr data. 3 proton singlet at this, it indicate presence of CH3, that is also there. So we can easily deduce the structure. You just connect them. Since ketone, it should come in between. So the compound is only this. What is the name of this compound? This is acetophenone. Now let us complete the justification. This is explained. This is explained. What about this peak? At 3000 there is a peak. Somewhere near 3000 or maybe just below 3000. That is due to the CH stretching of sp3 carbon. Okay? CH stretching of sp3 carbon, that is this methyl group. Then in the Nmr data, this singlet is verified. What is left over? 5 proton multiplet. That is the aromatic protons. You know that aromatic protons are highly de-shielded due to the anisotropic effect, and the chemical shift value comes between 6 to 9. Here it is 7 to 8. So that also tell you the compound is aromatic. Okay, so you have to have a holistic approach. You should look IR data as well as NMR data at the beginning and come to a certain generalization and then take one by one. Finally, after you arrive at the structure, you should again get back to the data and get convinced, get correlated. So this is the compound. And this aromatic proton appear as a multiplet because, you know, due to the presence of this group, all these protons are now becoming non-equivalent. Like this is A, this is B, and this is C. So there will be 3 signals in the aromatic region, and that will also undergo coupling, giving a very complex multiplet, right? So that's why it is a 5 proton multiplet. So this is how we solve combined spectroscopic problems. Practice more. Thank you.